This presentation is going to look at the evidence or clues that we have to the evolution of the universe. We're going to focus on those clues and observations, but not on the explanations that scientists have came up with for those clues. The presentation is inspired by Chapter 5 from Your Cosmic Context by Duncan and Tyler. Just to start with this intro slide, this is a woodcut that depicts an Aristotelian conception of the universe that preceded models of Copernicus. Let's start with the Olbers paradox. Simple observations of the night sky oppose the conclusion that we are in an infinite universe full of galaxies in every direction. According to Olbers paradox, if there were stars in every direction, we would see a bright sky. So therefore, the universe must either be A, not infinite, B, not full of galaxies, or C, capable of hiding light from some galaxies. So that's an initial clue that there's more going on to the universe than one would think. A major clue is the redshifts of galaxies. Just a quick note about this slide. This was taken by, this is a Hubble Ultra Deep Field. So they used this to detect galaxies that were so distant that it took the light that left these galaxies up to 13 billion years to arrive at the Hubble telescope. One of the things that they found when they observed is that there's hundreds of galaxies that occurred about 900 million years after the Big Bang, but before that, when they looked deeper, they found far fewer. So what that shows is that there's some evidence that supports a hierarchical model of galaxy formation, where larger galaxies emerged as smaller galaxies collided and combined. But as far as the clues that we want to talk about, we want to talk more about the redshift of galaxies. So to understand that, you need to know what the Doppler effect is. So the Doppler effect shows that or is a phenomena that happens as a source of a wave is moving. So the frequency of a wave increases as an object moves towards you and decreases as it moves away from you. So in other words, it shifts towards the red end of the spectrum as the source moves away from you, and towards the blue end as it moves towards you. And a larger shift corresponds to a higher velocity. Vesto Slipher of Lowell Observatory measured the redshifts of 25 galaxies between 1912 and 1917. Out of all of these galaxies, only 4 were blue shifted. So 4 of them were moving towards us, and the other 21 were moving away from us. A decade later, Edwin Hubble combined this redshift data with his own distance measurements and found a linear relationship. Objects that are further away from us are moving away from us with a higher velocity. The galaxies in the Virgo cluster on this diagram are impacted by each other's gravity and don't necessarily fit that linear relationship. Data from the Hubble telescope was used very recently in 2009 to give us a value for the Hubble constant of about 74 kilometers per second per megaparsec. The next clue that we have about the evolution of the universe is distribution of galaxies. This image here is from the Sloan Digital Sky Survey. In this image, the Earth is at the center, and each point represents a galaxy. Each galaxy typically contains about 100 billion stars. They're color-coded by age, so the galaxies that are more of a reddish color are older than the other ones. And you can notice a few things from this diagram. On large scales, the galaxies are arranged in dense clusters, and clusters are arranged into walls. There are voids between these walls. The pattern is not random. Clusters, walls, and voids are similar sizes everywhere. There is no evidence of larger structures than these walls and voids. And finally, there is no evidence of a center or an edge. One thing to note is the wedge-shaped pieces were not observed by the Sloan Digital Sky Survey because they're obscured by dust from the Milky Way. The next clue that we have is that there are microwaves that come from every direction in space. This microwave radiation was discovered in 1964 by radio astronomers Arno Penzias and Robert Wilson. They found that this background radiation was in the microwave band of the electromagnetic spectrum and was found everywhere they looked in the night sky. The peak wavelength of this radiation corresponds to a temperature of about 2.7 Kelvin. The radiation appears to come from a single source, but that source is in every direction. Any theory that we have for the evolution of the universe must account for that background radiation. This image compares observations made by Penzias and Wilson, the COBE telescope, and the WMAP telescope. The observations show variations by a few thousandths of a Kelvin from the average. The European Planck telescope, launched in the spring of 2009, will give us even more precise measurements of this cosmic background radiation. The next clue is that everything in the universe is made from common elements. Scientists can measure the abundances of elements and their isotopes in objects throughout the universe. From these measurements, we know that the abundance of elements is approximately 74% hydrogen, 24% helium, and 2% everything else. Any theory explaining the evolution of the universe must be able to explain this. Additionally, scientists know that lithium-7 was formed early and everywhere, because it is found in very old stars in every direction. But beryllium and boron were not. Any theory must also explain this specific observation. The final piece of evidence that we have is a comparison of astronomical ages. There are a lot of different ways that we can gauge the age of objects in the universe. One of these is radiometric dating of stars. So we can use the relative abundances of isotopes in stars to measure the age of stars. A 2001 study using abundances of uranium isotopes show that the oldest stars are between 9.5 and 15.5 billion years old. The next message is looking at the ages of star clusters. All stars in a cluster form at about the same time. Scientists have a well-established understanding of how luminosity, surface temperature, and spectroscopic features change at the end of a star's life. Scientists also have established a relationship between a star's mass and its lifetime. Using these characteristics, the age of the oldest observed star clusters is between 11 and 13 billion years. Scientists can also look at ages of the oldest white stars, or white dwarf stars. Cooling rates of white dwarfs can also be used within theoretical models to estimate their age. This image this image is from the Hubble Space Telescope and shows the oldest white dwarfs in the M4 globular cluster. These stars are between 12 and 13 billion years old. Since all of these measurements are similar, we have some confidence in our measurement. If nothing is older than 13 billion years, perhaps the universe is that young too. If the universe has an age, then it must have a beginning. Of course, it is possible that the universe has been around forever, but objects only started appearing 13 billion years ago. Any theory that explains the universe must explain these observations. All but the closest galaxies are moving away from us, and the farthest galaxies recede the fastest. On large scales, galaxies form structures of walls and voids. While background radiation appears to come from a single source located in every direction. Everything in the universe is made of the same elements. Abundances of light elements seem to be fixed long ago, and the oldest objects in the universe are about 12 to 13 billion years old.